Okay, so we're going to talk about Schrodinger's equation and unitary operations today. So, well, just to give a bit of, little bit of introduction before we really start the slides. So, I mean, Schrodinger's equation is like the central equation in all of quantum mechanics. So it's actually a super important part of quantum mechanics, and it's actually often the first thing that you might even encounter. But actually, we're not going to do it in the way that is normally done in courses. So normally, when you do Schrodinger's equation, the normal way that people present it is by like a differential equation and using a wave function. But actually in this course, we're not really going to use any wave functions like, like a scalar wave function. We're only going to use these kind of vectors as we've got here. So, we've got this state psi, and then we treat the state always as a vector and not as this like, scalar function, which is the wave function. So we're not actually going to do it like the usual way, but I think this is more appropriate for what we are trying to do. And eventually this will lead on right to quantum gates, which is actually sort of where we want to get up to. Okay, so okay. So so what is this Schrodinger equation about? Basically, it's all about time evolution. Okay, so up until this point, we've just considered this wave function to be just not changing in time. Like time has never entered into anything that we've talked about. We've always just talked about here's the wave function, and we're performing various operations like taking the expectation value, or maybe we're performing measurement on it, but basically nothing was ever really changing in time. Okay, so that's the new thing that we're going to include basically today, that things are going to this wave function is just going to change in time. And so far, basically, the only type of change in wave function that we've seen is that is through measurement, right? So we start with some state, and then we measure it, and then the wave function changed. Okay, so it changed randomly into, say, 0 or 1 in this example. But this is not the only way that the wave function can change. In fact, this is really more of a special case, and there's a much more common way that states actually change, and this is basically well, it's very much like what we just do.
Light network or
Processing your connection is poor.
Okay, yeah, you guys are frozen. Just checking my VPNs and everything. Well, what if I turn my VPN off? I think for Zoom you don't need it.
I think it's better now.
Okay. All right. So I've turned my VPN off. It might speed things up. Okay. So I was saying basically how do we include the time variation into wave function? So let's think about like what we do in classical physics, which is if you say consider this example where you're kicking a ball. So in this case, in classical physics, the kind of thing you might do is that you say, all right, well, at each point in time, this ball has some position and also has some velocity. And the velocity, of course, changes with time, as does the position. Right? So basically, all we do is that we've got a kind of a time varying function for the position and the velocity, right? So we just sort of add a, brackets t to all these things, and then, well, now it's time varying quantity, right? So for each point in time, there's a different position and velocity. So basically, it works the same way in quantum mechanics. So the wave function, basically, if it's time varying, all that changes is that the wave function is, the vector itself is a time varying vector. So the vector, some time might be pointing this way, another time might be pointing another way, and just depending on the time, it will, be a different vector. So the vector, you can think of it, but the vector has some time varying parameter to it, or you could say that, if you're expanding this vector in terms of time, then basically these coefficients. So here these are this is like the axes, right? So you've got some axes which specify the state. So these are not time varying. So if you've got states like 0, 1, and then 2, then basically your coordinates would not be changing. But then when you have your vector, which is your state here, if this is time varying, then this state will be swinging around over time like this, and then so some later time, t plus, why am I using a pen? I can just write on the screen. So yeah, t plus delta t, will change, and of course at this point, like all the coordinates of this state will be changing, right? So sorry, it's a bit hard to draw, but if you find the projections of this state to the states 1, 2, and 3, then these coefficients are all going to be changing. Okay, but at any point in time, the state should always be normalized. So if you freeze it at some time, then the state is always normalized. So the inner product with itself is 1. Or, of course, we can write this same thing in terms of the coefficients by basically substituting this into here. So if you do that, then you'll find, okay, n, a, n star, n, okay, this, a, we'll put a different label, m, on it because this is a different sum. And then if you do this, then because these guys only, this gives Kronecker product n and m. So what you'll get is just a sum over n, because the only time that these two are non-zero are if n is equal to m. So basically you'll have a n times a n, and then that gives mod a n. So this thing should be equal to 1. So so basically, this is how we include our time dependence. And so you might wonder, okay, so is this state changing just because something natural is making it change, or or in fact, what is making the state change in the first place? Now, basically, there can be two situations which are somewhat, you don't sort of arbitrary how you think of it, but just like in the case of this ball being kicked, this ball is moving like this because this guy came along and kicked it, right? So because of him kicking it, that has, altered the state and the trajectory of the ball, right? So this change in the state of this ball has happened directly because a person has come along and done something to it, and the time varying aspect of it, is kind of man-made, if you like, right? Or I mean, basically, if we were thinking about, say, planets and the moon and things like that, that's not a man-made effect. That's just happened sort of naturally. And so either way, basically, these states can evolve in time, either because humans did it, or it's just naturally doing it. And either way, you can basically describe it in the same way. So the quantum mechanics is exactly the same. So the state can be time evolving because just naturally is doing that, or you can make the state evolve directly by doing certain things to some quantum systems. So there's no difference in terms of basically like the origins of like why things are time evolving. It can either come from natural or sort of human means. Okay. All right. So that's how we take into account of this time evolution. So now let's look at exactly what is this sort of way that the time evolution happens. Okay. So in classical physics, as if you done any physics at some point, then you would have learned about Newton's laws. So F equals ma is kind of like your central, most important law of physics, or classical physics, right? So using F equals ma, in principle, you can sort of work out how anything kind of moves. So in the case of the ball, this guy applies some force, and then the force makes it move according to F equals ma, and then it moves this way because it's a force of gravity acting on it that causes acceleration, and you work it out like that. So what is kind of the law that happens, or that we use in quantum physics? Well, the same kind of thing is what Schrodinger's equation. This is the role that Schrodinger equation plays. So the way that it's normally written, it looks like this. It doesn't look anything like F equals ma. It's not the same law, by the way. I'm just contrasting the roles that these things play, and it's not the same. You can't match them at all, actually, in fact. So Schrodinger's equation is like the central law, and it looks like this. So it has this sort of time derivative, and has this thing called a Hamiltonian, which we're going to talk about in a minute. And this is the normal way that people write it. So something involving derivative and this thing Hamiltonian, which I haven't explained, but I'll get to that. But actually, an equivalent way that this can be written is like this. And so this is the one that we're actually going to use. Okay. So even though this is the more common one, this is the one that we're going to use. Okay. Now I'm going to explain what all this stuff means in a minute. But just for now, all I want you to understand is that basically the whole, point of Schrodinger's equation is to figure out what time evolution is. So just like in the ball example, where you're given some initial condition, so you might be told, okay, the ball is sitting here, weighs 1 kilogram, and I kick it with this force, and then it flies through the air, and the acceleration due to gravity is 9.8. And the question might say something like, figure out where the ball lands, or something like this. So basically what you're trying to do here is you have some initial condition, and from the initial condition, you use the law that you're given, Newton's law, to work out what's going to happen to the ball later on, right? So, given an initial condition, use the law, and then you find the final result. What we're doing here is exactly the same as that. So basically, Schrodinger's equation, what it does is you're given an initial state. So you know what the initial quantum state is. The law that we're going to use in this case is Schrodinger's equation. So that's the thing that's going to, it's the machinery to tell you what's going to happen to it later on in time. And the kind of physical conditions that you have for the particular situation are in this Hamiltonian, which I'll explain in a minute. And basically, you do your maths, and then at the end, you find out what the state is some later point in time. So actually, conceptually, what we're doing is very similar actually in classical physics. It's just that we've just got a different law. Instead of Newton's law, we're going to use Schrodinger's equation. Instead of using position and momentum as your initial state, we're going to use a wave function. But overall, the kind of scheme of what we're going to do is the same. Okay. All right. So now I hope you have an overall picture. So let's now dive into what actually this equation really means. Okay. So let's break down Schrodinger's equation. Okay. So what is this thing? To the right position. Yeah. Okay. So let's break it down. Let's look at this form with this exponential. Okay. So this is our initial state. That's the state that we start with, and this is the final state, the thing that we're trying to work out. Okay. So what's all this stuff here? So exponential, obviously, that's just e. Okay. Euler's constant, basically. I is, of course, square root of -1. This t is time, and we can use seconds for the time. So that's basically how much time we're going to evolve it forward for. So here's our initial state. We're going to evolve it forward in time for some amount of time t, and that's the final time. H bar, this thing is called H bar, which is H bar is actually h divided by 2 pi. And what is h? H is Planck's constant, and again, that's just some kind of number. Okay, so this is just some number. So actually, all this stuff here is not particularly complicated. All the stuff that's really important here is in this thing, H, which is the so-called Hamiltonian. So what is this thing? So this is actually a matrix, okay? So all these other things were scalars. So t is a scalar, it's just number. I, okay, it's a complex number, but it's still a scalar. H bar is a scalar. But H is a matrix, okay? H is some matrix. And the size of the matrix is the same as the dimension of this vector. Okay, so say this is a qubit. Okay, so this vector would be like a length 2 vector. In that case, this Hamiltonian is a 2 by 2 matrix. Okay, so kind of maybe I should say that this one, you should think of it as a matrix. So, well, like this. And this state you should think of as a vector, okay? And of course, the final state is also a vector like this. So, all right.
A matrix.
Yes.
Exponential.
Yes, good question. Yes, we'll get to that. Yes, exactly. So it is, this Hamiltonian is a matrix, but we're actually putting the matrix within the exponential. So it's exponential to the power of a matrix. Okay, so we'll have to understand exactly what that means later. we'll get to that point, but first let's understand what kind of a matrix this H is. So this matrix H is a thing that actually tells us sort of the physical conditions that this system is in. So usually, well, I mean, no, actually always, this state is talking about some physical system, right? So maybe it's like an atom or something. And, this state is talking about how, these atoms, has different levels. And, that's basically what this vector is talking about, right? But just having a vector doesn't really say what kind of physical conditions that atom is in. So, for example, if you just write down this vector, it doesn't tell you that, for example, maybe this state has a pretty high energy and this state has a low energy, right? That's just sort of one kind of example, as we're going to see. But basically, what this Hamiltonian is telling you is the kind of energy structure to the whole problem. Okay? So this Hamiltonian is, it has this definition here, and basically it's a matrix which is, well, if we write this in matrix form, so it would look like this. So it is matrix where it's like E0, E1, E2, and so forth. Okay. And all these elements would be 0. Now, so this looks simple enough where it's like, okay, you just put in the values of the energy into the diagonal elements, right? Now, this is actually a little bit more complicated than it looks, because actually these states here, so perhaps, if I wrote down this state here, this state, I might write something like psi n, like this, right? So, perhaps this is, okay, well, let's be a little bit more specific and say what time is. So, say at time 0, my state is like this, right? And maybe I'll put a 0 here. So initial state is some kind of state written like this. Now, the point is that actually, whoops, sorry. Point is that this state here, the basis states here, may not necessarily be the same states as what's in this Hamiltonian. Okay, so when I write down this this matrix here, actually we also have to think about what basis this matrix is written in. So maybe this first matrix, this first vector is this state E0, and the second one is E1, and so forth. Now, those states might not actually be the same basis as the states that I just wrote my state in. Okay, so this is where actually things get a little bit more complicated than things can get a bit more complicated. But we're going to show you. I'll show you a couple of examples so that we'll sort of we'll walk through it. But ultimately, any Hamiltonian you should be able to write down in this form, where it's basically takes this form where it tells you, what states have like what energy. Okay, so ultimately this Hamiltonian is saying, okay, well, this state has this energy E0, so the state E0 has energy E0, state E1 has energy E1, and so forth. And basically this energy structure is kind of the information that you need to provide to specify the physical conditions that is going to tell you how this state is going to evolve. Okay. All right. It's probably sounding a bit too abstract at this point. So let's see if I can give you a couple of examples. Okay. So here are a couple of examples for qubits. So if you ever do physics, which I know not all of you are physics majors, but there is a particular effect where if you apply a magnetic field to an atom, then the energy levels actually change. Okay, so just imagine you have an atom here, and then you have various energy levels of the atom. Then if you bring a magnet close to it, then what people see is that these energy levels can sort of move apart. So this is one example of a possible Hamiltonian, because it basically tells you what kind of physical conditions this atom is in, and tells you like what energy levels that you have. So if we just sort of follow this general form on the previous slide, so basically the Hamiltonian is like, okay, so this state has this energy, and then you form a matrix that looks like this. Okay? So whatever that energy there is, that's the number that sits out in front of this outer product of these two states. So suppose in this case, the state 0 has the energy minus b, and b is just some number. Okay? And then suppose the state 1 had energy plus b. So we would construct this Hamiltonian matrix in this way. And so it'll look like this. It'll be minus b, that's the coefficient of the state 0, outer product 0, b plus b was 1, outer product 1. And if you like, we can write it in matrix form, and it would look like this. And if you like, or again, we can rewrite it in terms of this Z matrix that we've been using sometimes up until this point, because this matrix here is actually just Z, right? So I might write it also like this. These are just all equivalent ways of writing it, and choose the one that you like the best. Maybe one thing that you need to be careful of when you use this notation is you need to keep a mental record of like what quantities are actually matrices and what quantities are scalars, right? So in this case, Z is a matrix and then B is a scalar. So you have to sort of, I guess, remember that. But at least it's very compact. Okay. Okay, so that's fairly straightforward, and so that's how you construct the Hamiltonian in this case. But as I was saying in the previous slide, it's not always, it doesn't always have to be so simple, because actually these states E, in principle, could be anything. They just have to be orthogonal to each other. So here's another example, this time when the states are not just the simple form. So for example, again, I'm not really going to explain why or anything in terms of physics, but another example is, say you shine a laser, it's tuned to the right frequency, onto an atom. Now, it turns out that what this does is that it, again, makes two states, assigns two states different energy. But it turns out that the states are not just 0, 1. In fact, they're so-called plus and minus states, which I didn't write here, but, well, I guess I'll rewrite it, which is that plus or minus is the 1/√2, it's a superposition state. So basically, depending on the physical conditions, it's not just like 0 and 1 states that you can have different energies. You can actually have some other states which are, some set to some energy. And for example, in this case, well, the way that you'd write down the state is just like what we did above. Here's the energy of that particular state. Why did I? Okay, I don't know. I don't know why I didn't have the minus sign here. I think this should have a minus sign here. And this should be plus. So this should be minus, and this should be plus, and then so I guess there should be a minus sign. So out by overall minus sign. But basically the way that we're doing it, it's the same. We have the state, we have the energy of that state, and then again we've got the state, the energy. And what's interesting in this case is that the Hamiltonian is now off diagonal. Okay. And we'll see how that actually makes a difference. Well, you can see that this will form different types of Hamiltonians, which not necessarily actually diagonal. So even though I said over in the previous slide that this Hamiltonian is diagonal. So if you remember over here, I said that this Hamiltonian is diagonal. So it depends on what basis you're looking. So this is not diagonal here because, for example, if I wrote this in the original basis, in the plus minus basis, right? So if I wrote this in plus minus, minus. Now, of course, in that basis, this will be diagonal, right? So this will be like that, right? But because now if I want to write it in the 0, 1 basis, it becomes off diagonal. So, whether a Hamiltonian, like Hamiltonian or any matrix in general, whether it's diagonal or off diagonal, it completely depends upon what basis that you write it in, right? So, there is always some basis where you can write it as diagonal, but in the context of another basis, it may not be diagonal. Any questions at this point? Okay, all right. Okay, well, I hope that was reasonably clear. Anyway, we haven't finished yet, so still opportunities to ask questions. Fine. So, we're still going through breaking down this Schrodinger equation and kind of breaking it down into pieces. So, we've got a bunch of scalars here. There's an I, there's a matrix here. And I've told you basically what this H matrix is, Hamiltonian, and basically the way that you construct it like this. So now let's talk about what Judy just asked, which is, so you have a matrix in the exponent. So what does that even mean? So matrix exponentiation is defined as in the same way as I think, well, okay, I'm not quite sure the definition of e to the x is, but this is certainly one way to write the exponential function, right? So we can always write an exponential function as a Taylor series. So have you guys, you've seen this before, I hope? Right. Yes. Yeah. So we can perform a Taylor expansion of the exponential function, and then it looks like this: 1 plus x squared 2, and so forth. So this is how we're going to define matrix exponentiation. So because if you have a matrix here, so let's just start with, forget let's all these constants here. So if you got a matrix M, then we can just define it in this way, because a product of a matrix is well defined. We know how to do, the square of a matrix. It's just M times M and M cubed and so forth. So because that is well defined, we are able to perform, well, the right-hand side of this is well defined. Okay, we have an infinite series of these matrices. However, in many cases that we're going to do, we can actually sort of sum up that series and then figure out what the final result would be. So if you have e to the m, it's basically defined like this. If you use things like Mathematica, do you guys use Mathematica?
Not yet.
Not yet. All right. So, there are ways of evaluating matrix exponentials. Well, maybe I can show you later if you're interested. But basically, it's a kind of a standard sort of procedure that you can do this. It's not a extremely exotic thing. Performing matrix exponentiation is a sort of a task that is often required in many areas of well, physics, engineering. Okay, so that's matrix exponentiation. That's how it's defined. Now, if you have an I there, what does that do? Because actually, that's the situation that we have here. The constants, well, I think it's not that bad, because you can appreciate that you can just absorb that into the matrix itself. But if you got this I here, what it basically does is that it starts to introduce i's, of course, into the power here, because just here you got m im, but here you got im squared, and I squared is -1. Here you're going to have I cubed, which is minus I, and so forth. So you can kind of see here that actually you're going to have all the odd terms have an I for the m, and all the even terms have actually m. Maybe one thing I forgot to mention about the Hamiltonian matrix is that actually these energies are always real. Okay. So because these energies are always real, it actually also means that this is a Hermitian matrix. So that means that if you did H dagger, it will be equal to H. And this is kind of important, because Hermitian matrices, this kind of guarantees that the eigenvalues are always real. And because we're talking about like a physical system, and it's not really a very good meaning to an imaginary energy, we kind of need to have this property of this Hamiltonian, because if we don't have this property, then we might have like imaginary energies, and it doesn't really make sense. Well, at least for now. Yeah. Okay, so why did I just tell you that? Well, I just told you that because basically, you can think of in this series, well, this H here is sort of a kind of, it's real. Okay, so there's that when you diagonalize it, there's no imaginary numbers. So this means that the only imaginary term in this whole exponent is from this I that's sitting there. Okay, so when I did this expansion here, I'm kind of implicitly thinking that m and m squared, these are all kind of real. And the only part that's imaginary is coming from this I. So this is why basically I can really say that the even terms are going to be real, purely real. And then all the odd terms are going to be purely imaginary. Okay, so that's what matrix exponentiation means. So basically that I think is, well, at least taught you how it sort of works, but probably you need a few examples to figure out how to actually do calculations with it. So let's do a couple of simple calculations to show you actually how you work out this kind of time evolution. So let's look at this example, which is, let's say the Hamiltonian is the first example that I had before, which is this h is equal to minus b times z, and the z matrix is that usual z that we always have. Physically, it's something that's like this. And let's try and apply Schrodinger's equation and work out what the state of something is sometime. Say initially the state is this thing, alpha beta. And let's try and work out what the state is going to be sometime t later for this particular Hamiltonian. And then so what we're going to have to do, we're going to have to work out what this quantity here is, perform this matrix exponentiation, and apply it to here. So, well, I've got the answer here, but let me just go through it on the whiteboard so that you can sort of see it step by step. Okay. So, okay. Just want to get this in the right position. Okay. Okay, so all right, so let's do that calculation. Okay, so initial state I've said is alpha beta. Okay, so that's our initial state, and Schrodinger's equation says that the final state is going to be e to the minus I of h t, on h bar, and then multiplied by the initial state. Okay, and the Hamiltonian that we're going to use in this case is minus bz, which written in matrix form, it's going to be minus b plus b 0 0. Okay, so that's the problem. Okay, now the way that we're going to do this is we're going to first, let's try and work out what this thing here is. And this thing here, even though it's matrix exponentiated, it's basically ultimately still a 2x2 matrix. Okay, so this thing actually is a 2x2 matrix. We just have to work out what the 2x2 matrix is. Okay, so okay, so let's try and evaluate it. Okay, so sorry, I'm just trying to think of a good way to, well, okay, firstly, let's just substitute the Hamiltonian that we have into here. So we've got minus I h t, so we're going to substitute the h in there. The I is going to be still there, but the minus sign cancels. It's going to be BT on H bar times by Z. Okay. So this thing here is a matrix here. This Z here is a matrix here, but this stuff here is a constant. So I'm just going to call this all this constant stuff. I'm just going to call that X because okay, maybe I won't call it X actually. I'm going to call it tau, where I'm going to define tau is going to be equal to just this bunch of constants, so I don't have to keep on writing it all the time. Okay, so it's going to be e to the I tau of Z. Okay, now so all right, so now let's do the matrix expansion according to the definition. Okay, so this is e to the I t z. So what I've said before, 1 plus I of tau z plus I tau z squared tau z cubed to 3 factorial. Okay, and it keeps on going, but let's stop there. Okay, now what we've got here now is actually powers of this Z matrix. Okay, so let's just work out what the power of, okay, well, maybe you guys can help me here. So maybe someone to remember Z is this, whoops, maybe somebody can tell me what is Z squared?
Identity.
Right, very good. So Z squared is actually identity because, well, when you have a diagonal matrix, actually doing the powers is kind of easy, right? So you just multiply the, you just square the diagonal elements. And 1, because -1 squared is 1, this is actually just identity. Okay. What about Z cubed? What's that going to be?
Just Z.
Just Z.
Yep, just Z, because Z cubed is Z squared plus Z, and Z squared is identity, so it's just Z. Okay, so we can see a pattern emerging here because basically all the even powers are all going to just give identity, right? Because Z4 is just Z squared, and that's just identity. So basically all the odd powers are just Z, even powers are just I. So what we can do here is to kind of, say that, we can do here is to kind of look at the even and the odd powers and separate them out. Okay, so we're going to have 1 plus I t over, I t squared 2, then dot, dot, dot. And all this will be actually identity. And the odd powers are going to be IT plus IT cubed 3 factorial dot, dot, dot. And all these are going to be Z, right? Okay, now, can anybody spot a nice way to write all this?
Well, like for the top left corner, it would just be like 1 plus I tau plus I tau squared divided by 2 until which is the exponential of I tau and the
I tau. Okay, hold on. Let me. I think you're on the right track there. But let's see what we get. So
Is it like cosine and sine?
Yes, exactly, yes. Yes, so if you think about what the exponential of e to the tau is, it's going to be 1 plus tau squared onto something, something, right? Actually, what we've got here is this part is actually going to be 1 minus tau squared onto dot, 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 dot. This one, we can factorize the I. Sorry. Factorize the I, and then we've got tau plus, and then I cubed is also minus 1 or minus I. Minus I. So this will be tau cubed on 3 factorial dot, 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 z, right? Very messy. Okay. So it's, yeah, e to the tau is close, but it's not really exactly what we want, because that would be all the powers and also doesn't have this I thing in it. But, you know, e to the e to the I tau, of course, it looks a lot like what we've got here. It's the I tau, and then this will be minus sign, so forth. And as we know, this thing can be written as cosine t plus I sine t. And cosine t only has even powers of tau, right? So if you do a Taylor expansion of cosine, cosine gives it actually exactly this stuff here. So cosine is like expansion. Cosine expansion is 1 minus tau squared over 2, and sine expansion is tau minus, right? Yeah, I think that's right. Yeah. Curves this way. So yeah. Okay. Tau minus tau cubed over 3 factorial. So basically, the trick is that you can write all this stuff here. All this stuff here is cosine tau, and all this stuff here is sine tau. Okay. So okay. So then might be just easier. Everybody fine with what I've written here? I'm just going to erase it now. So, okay. If you're fine. Okay. So, so basically, okay. Erase it if I did. No, yes, I will. Sorry. This is so all very hard with Zoom, right? So e to the I tau z, basically the final result is that it's cosine tau plus I sine tau z. Okay, so this looks a lot like Euler's formula, where you have the cosine and sine expansion, but if you have a matrix in there, then basically only the sine has this matrix, and sorry, this sine is only got the tau in it here, right? So it's like this. And so now we can actually write it, now that the matrix is actually outside of the sine and the cosine and the exponential, we can actually really write it as a matrix, a 2 by 2 matrix. and it will look like this. Oh, sorry. Sorry, excuse me. So I t, this is 0, this is 0, this is cosine t. Then because z, the bottom one is actually minus, looks like this. And actually we can even write this as a in terms of the Euler's function again. So that's basically what the matrix exponentiation step. That's how you can evaluate it. And once we've written it like this, then our job is actually pretty easy. Okay, so then now let's perform the final step, which is just to multiply this state. Multiply the initial state by this matrix. So all we've got to do here is got the state here. Okay, well, maybe I will clear it again. So what we want to do is we've got the final state is e to the minus h t over h bar state. And we eventually worked out that this matrix here is actually just e to the I of tau, e to the minus I tau, 0, 0. This initial state is alpha beta. Just do the matrix matrix multiplication. And tau, if you remember, is just bt over h bar. Okay. So that's the final result. So basically what happens here is, in this case, is that the numbers, if you start with alpha and beta, they just pick up some complex phase here, and basically this will evolve the state in, in time. And this tau here is just related to the real time according to just some, these coefficients like b and the h bar. And these are just some physical numbers that you can just plug in, and this is your state evolution. So okay, we can just quickly go back just to finish up the. Just have a look at the slide. Yeah. So basically. So the final state here is what we have at the bottom here, and that's how it changes in time. So I think maybe we'll leave the next example for the next lecture. But basically, what we're going to have is something kind of similar, except that the Hamiltonian is going to be different. So x is going to be the new Hamiltonian. And then, so we're going to see a slightly different type of time evolution of the state. Okay. Any questions? All right. Okay, then we'll leave it there, and I will see you on Thursday. And don't forget to tell me if you have any problems with the assignment presentation dates.